Okay guys, here we're going to review a little bit our circular trigonometry, and so that would be central angles and circles. I suppose the primary sketch that would be worth making here, and I don't even know if I need my axes necessarily. If we had a central angle in a circle, so originating from the center of the circle here, and we said this circle is of radius r, so like this would be r and this would be r here, and our angle would be theta. We always intercept an arc length here, and our intercepted arc length is what we classify as s. So some things. Previously, when we investigated, what are radians? Radians are kind of just a measurement here of our angle that tells us how many times the radius fits around through the arc length. And so, the bigger your central angle is, the more times the radius length would fit around the outside. It kind of makes a reasonable way of thinking about our angles here. So the very first kind of expression or equation I want to make sure we write down is just simply this. This is our angle, okay? Angle in radians. The angle in radians kind of literally tells us how many times the radius fits into the arc length here. This kind of leads us to a couple of really nice conclusions though. And the first one is just this. If we say we knew the radius of the circle and we knew our angle, we could actually solve for the arc length s here. And the way we do that is just to take this original equation and multiply both sides by r. So we end up with our arc length equation. Okay, and our arc length equation is just s equals our angle times our radius. And just to be clear here, r must be in radians. Okay, this has to be the case here. The other formula that we tend to look at is also related. I don't have a derivation for you, but I can tell you this is our sector area. We say the area of this sector that we kind of have in our central angle here of a circle of radius r is 1/2 theta r squared. So we square the r, we put a half as our coefficient in front of our angle, but it's still kind of theta times r. And again, this is also very true. Theta must be in radians, okay? The other measurements that we explored as we looked at these central angles, they dealt with velocities, okay? So as far as velocities are concerned, we have two types of velocity that we looked at here, and I want to start with I feel like the simpler of the two, angular velocity, okay? And we also have linear velocity as far as our velocities are concerned here. So our angular velocity, well, what are we talking about? Well, we're talking about things moving around in a circular path here. So if I had an object moving around the outside of this circle at a uniform rate, I could track how much the angle is changing over time. And we tend to do that in radians as well. But, just to kind of state the obvious then, our undercase Greek letter omega, which is angular velocity, is just the change in angle over the change in time here. Little bit different. When we talk about linear velocity, we're actually talking about the distance that this object covers around the outside of the circle over time. So distance over time is linear velocity, but our distance here is our arc length. And so we could sum this up as just saying that our linear velocity is our arc length covered over time, or distance over time. It's worth noting that, again, our arc length is just our angle times our radius value. So arc length s can be written as theta r over time, and it just goes to show that we need some values here. We often need to know the angle, the radius, and the time, but a little bit of plug and chug. So looking at number 3 here, I'm reading it says a wheel with a radius of 24 inches rotates at a rate of 250 RPMs. How fast does the wheel roll in miles per hour? And the first thing I notice is it's asking me how much my distance is changing over time. And so this must be our linear velocity, and if I study my formulas here, I know this is arc length theta r over time. It means I need 3 things here. I need theta, r, and time, and we're just going to go plug and chug. So as far as these things go, I think 24 inches was clearly our radius. It didn't say diameter. Our angle, now I notice that it rotates through 250 revolutions, so I'm going to just kind of write revolutions, and then time, this was RPM, and I kind of just wrote this out here, but sometimes you see it RPM, and we imply that the time here is then just 1 minute. The neat thing about this is we have everything we need to go plug in. Our angle needs to be in radians, and so recall that we talk about our 1 full rotation right here. That is a 2 pi rotation. Okay, so for every revolution we do, it's 2 pi radians. Well, if we have 250 revolutions, we'll take that times 2 pi rad per revolution. You don't have to write the units per se, but we do get 500 pi, and this would now be in radians, no longer in revolutions. So if we've got everything we need, let's go ahead and write this out then. I think that our linear velocity would be our angle, 500 pi rad, okay, times the radius length, 24, okay, that was in inches, And then we have our time here, 1 minute. The only thing is just we wanted to make sure we were in miles per hour. So we're already 100% correct. We're just in inches per minute. Let's change this miles to hour. Change it to miles per hour. So I'm going to start with my time. I know that if I want to go minutes to hours, my minutes are already downstairs. To get those to cancel out, I'm going to have to put minutes on top of this and hours here. And I know that it's 1 hour for every 60 minutes. Instantly, I'm going to go ahead and cross off our minutes here. But this just means we're in inches per hour now. Let's get our inches over then. Inches to be on bottom, if our inches are on top here. And we're going inches first. I like to go feet. So this would be 12 inches in 1 foot and cross off my inches. We're now in feet per hour, and there are 5,280 feet in 1 mile. So I'll put my feet down here so they cancel. 1 mile is 5,280 feet, so we can cross these off here. So, the tactic now would just be to go ahead and multiply these all straight across. And so, I'll grab my calculator here. I suppose that turn this sucker on. On top we get 500. Don't forget our factor of pi. 500 pi times 24 times 60 times 1 times 1. And if we take this answer, so divide this by, in parentheses, 1 times 12 times 5280. So 12 times 5280. Close off that parenthesis. We should have our rate, and it's about 35.70. So 35.70. Okay, and this is miles per hour. Okay, so just making sure that you're finding the right units, or finding the right values, putting them in the right units, and plugging and chugging, and then converting your units if necessary. Okay, if need be. Number 4 here, we just want to find the length of an arc on a circle with a radius of 11 meters and intercepted by a central angle of pi thirds. Well, hey, arc length is theta times r. So that just means we need our theta, we need our r. Our radius here is clearly 11 meters, and the central angle is pi thirds, and that looks like it's already in rad. So I'm going to go ahead and set up this expression and multiply. We have our angle, pi third rad, times 11 meters. I suppose that if we put our 11 over 1 and multiply straight across, we get 11 pi thirds. And because radians are essentially unitless, this is just in meters. And again, I want this out to 2 decimal places, so we'll just go ahead and real quick here, 11 pi divided by 3. It'd be roughly about 11.52. So about 11.52 meters. Cool. Cheers.